And the final type of figure that I'm going to be talking about is the histogram. And so here what we're dealing with is a continuous data set. So here we're revisiting the cherry trees, and it's split into groups that we call bins. I'll talk about that in a second. So what we're plotting is the frequency. So the frequency could be either counts, so here we've just got the number of trees, so 1, 2, 3, 4, 5, 6 trees, or sometimes it's the frequency density. Hold on, I want that room. But let's write that here. So that's frequency, so that's count, or something called frequency density, which is a proportion. So that could be the percentage of trees in a certain with a certain sort of heights. And it's okay, so we've got the frequency on the y-axis, and then we've got the bins corresponding to groupings of our continuous data set on the x-axis. And so here it's that, and we draw bars to represent that. And so two important things about these bars that differentiate them from bar charts. So it is purely the area of the bars that is important, not their height. And the second thing is that there are no gaps. Between the bars. Okay, so that's kind of the general outline. Those are the rules. So now let's work through this example. So here we've got the heights of all these different cherry trees. 31 different cherry trees have been measured, and we want to make that into a histogram so we can see the general distribution. That's what it's useful for. Let's write that down. Distribution of the data set. Simply hit this, another way of doing that. Cool, so now let's look at these 31 cherry trees. So a general rule is that the number of bins that we use should be about roughly the square root of n. So here n is 31, so roughly 31 is 5.5, therefore you use 5 or 6 bins. And that's important because we don't want there to be too much noise. If the bins are too small, there aren't enough samples in each one, and you can't really see the trend so easily. And if there aren't enough bins, like imagine we took a bin that was between 60 and 90 for this example, that would just be one big bar, and that wouldn't tell us anything either. So normally about the square root of n works out okay, but you've got to use your best judgment to see what looks most sensible. So here they've decided to use 6 bins, and how do we decide where they fall? So here we've got roughly between 60 and 90, so that's 30 feet difference. And then if we do 30 divided by 6, that gives us bins of 5 feet each, which sounds pretty sensible. So if we start at 60, so we'd have 60 1 and all the way up to 64.9, so 60.0 to 64.9. So we could put let's call A for the first bin. So you've got to be quite precise with exactly where your bins begin and end. So it's 65.0 and everything bigger to or equal than that is in B. And then, excuse me, 69.9. Okay, so let's divide these up now. So anything between 60 and 64.9, so that's all these guys. So that's a count of 3. So our first bar goes up to 3. And the second bin, anything between 65.0 and 69.9, so that's 1, 2, 3 again. .0 to 74.9. Let's call that bin C. That's all these guys, all the way up to 74.8. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So for some reason, some people like to make the ones at the end kind of shorter and fatter. But if you just make all the columns the same width, then that's probably the easiest way of getting that right.